Welcome to the Research Highlights video series. These videos are intended to provide a summary of some of the research being conducted by members of the Hopkins Group at the University of Waterloo. This video highlights some of our recent progress in studying the properties of B12F12 dianions. For a more detailed discussion of the properties of transition metal B12F12 clusters, please read our publication in the Journal of Physical Chemistry A. Our mission in this study was to explore the infrared photoinduced charge transfer properties of transition metal B12F12 clusters as we varied the transition metal cation. B12F12 2- has been identified as a weakly coordinating, or superweak, anion in the solid and solution phases. Consequently, it has been proposed as a component in sodium batteries and in highly reactive materials. When a cation binds to B12F12, the fluorine atoms act as a separating layer to increase the distance between the cage-centered negative charge and the metal-centered positive charge, thus reducing the electrostatic attraction. However, by increasing the size of the metal cation, we also increase the size of the cation valence accepting orbitals, thus increasing the HOMO-LUMO overlap and therefore propensity for charge transfer. To test this hypothesis, we prepared a number of transition metal B12F12 salts and attempted to study clusters of these species in the gas phase. We found that we could not produce clusters of very heavy metals and B12F12 anions. In the production process, the metal cations were neutralized, thus indicating charge transfer to be very efficient in these species. For lighter metals, like copper and nickel, we were able to produce and trap transition metal B12F12 clusters. When exciting these clusters via the boron cage T1U vibration, we found that we could induce fragmentation and concomitant charge transfer from the B12F12 cage to the metal cation. High-level quantum chemical calculations predict that charge transfer photodissociation is the dominant product channel for all of these species. IR excitation via the boron cage T1U vibrational mode enables excitation to the delocalized cluster LUMO, thus facilitating migration of electron density as the cluster dissociates. Whether or not these photophysical properties persist in the solid and solution phases is currently an open question. For more information about the Hopkins Group members and the research that we conduct, please visit the Research Group website, which is hosted by the University of Waterloo Department of Chemistry. Thank you for your time and your interest in our work. See you next time.